start with Allan, Denis on the characterization of giant planets with VLT HiRISE.
Faut attendre que ça se calme un peu. Alright, so can you hear me, everybody? Okay, perfect. So hi, everybody. I'm Allan. I'm a last year PhD student in Marseille. And so I will be presenting the work I've been doing on the characterization of giant planet at high spectral resolution with the VLT HiRISE instrument. So the VLT HiRISE instrument, it's a bit similar to KPIC actually. Is an instrument installed at the VLT, and the principle is that it combines the high contrast imager instrument sphere, here, with the high dispersion spectrograph instrument HiRISE Plus with a fiber bundle. So the principle is to get high resolution spectroscopy of exoplanets that are really faint and close in to their host star. And so the instrument has been under 6 years of development, and the first light was during summer 2023. So you can see here an example of the first astrophysical detection. And so the HiRISE instrument is an instrument in H-band only, but with a resolving power of 140,000, so which is a very high resolution. If you want to have more information about the HiRISE VLT results, you can have a look at the poster of Bhavesh was put on session 2. And so with HiRISE, we have observed around 25 exoplanets, and 2 of them are very emblematic, and I will present the result of these 2 exoplanets, so which are FLAB and 51RAB. So as you can see here, they share very similar properties in terms of temperature, mass, and size, but they also have their specificities, notably in terms of eccentricity. So IFLAP has a very low eccentricity, whereas 51RE has a very high estimated eccentricity, which is really interesting since it really tells a lot about the formation histories of this planet. So to analyze this data, I use the forward modeling code Formosa. So the principle of Formosa is to compare some data with a grid of self-consistent pre-computed atmospheres, models of atmosphere. So these models are really are now very common in the field of direct imaging, and some of them are publicly available. So there is the XORM, BT-Settle, Atmos, Sonora, and other grid available. And so the principle is to use a grid of parameters, so temperature, surface gravity, CTO ratio. And at each point of the grid, you have a model. And Formosa will interpolate between the point of the grid to generate a new model with very specific values for these parameters. And then you have another step specifically with this data, because HiRISE data are deeply contaminated by stellar speckles. So we have incorporated a high contrast module which jointly estimates the stellar speckles and the planetary signal so that we can compare properly the data to the model. And so at the end, through a log likelihood computation, we compare the data to the model, and the Formosa code outputs the corner plots, the radar plots, and the chain of posteriors. So I present more in details the result of FLAP planet. So the result I got with only the H-band HiRISE data. So we estimate a very supersolar metallicity and CTO ratio, which are really consistent with all previous low-resolution analysis, which is great because we are only using small H-band data at high spectral resolution. And so we have also clear detections of H2O, CH4, and tentative detection of CO. So these detections support the derivation of the CTO ratio, because the carbon mirroring molecules CH4 is clearly detected, and the hydrogen bearing molecule H2O is also clearly detected. And so we've seen that the results will clearly depend on the data extraction method. They are very different than the result I presented 1 year ago in my paper, because I've improved a lot of things in the pipeline of the data reduction. notably the extraction of the data and the wavelength calibration. And it tells us a lot about the importance of having robust reduction of the data. So we can tell something about the architecture of the planet. So if you use only the available astrometric data points, we have two families of orbit, depending on the radial velocity of the planet at a given epoch. These two families arise because the astrometric only gives us information about the sky projected orbit of the planet, but doesn't give us any information about the third dimensional the third dimension, which is whereas the planet is getting away from us or is getting toward us. And so adding the HiRISE Allan measurement, as I did here, we are able to rule out a whole family of orbital solutions, as you can see here. And so by doing so, we have the last ingredient to derive a full 3D orbital solution of the planet, which enables us to have the information of the phase curve of the planet at each epoch, which is particularly interesting for reflected light spectroscopy. We can also tell something about the rotation of the planet and the obliquity. Thanks to the vicinal measurement, we give constraint on the rotational velocity of the planet. And one thing particularly interesting is that if we can combine the vicinal measurement with some photometric variability, for example, with the James Webb Space Telescope, we would get both the rotation of the planet and also the obliquity of the planet, which tells a lot about the formation history of the planet. Now I will talk about the result I got on 51 AOEB planet. So similarly as for HiFLEP, we can constrain the orbit of the planet. This time we have 4 data points for the RV of the planet, extended over a 2-year baseline, and we have a detection of the planet at each of these points, which enables us to really constrain more the orbits of the planet, as you can see on this plot here. Similarly as for HiFLEP, we have, of course, the information of the phase of the planet. One thing particularly interesting is that we have also the eccentricity of the planet, which turns out to be very, very high, which tells a lot about the history of the planet. I will explain a bit more later. And one thing we can wonder is whereas 51 REB is favorable with the Roman Space Telescope because it is a target of great interest for this telescope. And so if we compute the reflected light contrast and compare it to the thermal light contrast, we have the conclusion that it is not favorable with the Roman Space Telescope because the contrast is really too low. But in band 1, in this band, the reflected light contrast overpowers the thermal light contrast, which means that this will be a target of interest for maybe for the VLT instrumentation, which will probe reflected light spectroscopy with reaching a higher contrast. If you look closely at the result of the RV and VCNI for the planet, we can see that there is a very inconsistent value for the VCNI, notably at the last epoch, which is very low. And actually, we realized that it was due to the fringes. So again, the fringes, sorry. So the fringes in the HiRISE instrument are coming from the dichroic filter, which act as a Fabry-Perot interferometer and generate oscillations in the sinusoidal oscillations of the stellar speckles, which we can see here. If you put the power spectrum density as a function of the resolution, we have a really big peak at a resolving power of around 25,000. So if we exclude if we are interested to talk more about why the fringes affect the vicinal measurement, I will be happy to discuss it more in detail with you. But now we are going to assume that we just reject the last epoch because the fringes of the last epoch are particularly important. And this is due to the fact that the last epoch is the epoch where the planet was the closest to the star. It was lower than 200 milliarcseconds in separation, which is really close. And so because of this proximity, the stellar speckles were really high. But we exclude this data set, and we can derive the vicinal measurement for the planet around 10 kilometers per second. And we can also, similarly as for HiFLEP, give constraint on the rotation period of the planet. Something also interesting is that we have a correlation between the RV uncertainty and the vicinal measurement, as we can see on the top right plot. And this is due to the fact that at low vicini, the effective resolution, which is defined as C divided by vicini of the template, will be higher. And it means that the variation of the log likelihood will be sharper when we shift around the RV of the planet. And it means that the uncertainty will tend to be lower at low vicini. So what can we say about the eccentricity of the planet? So one possible scenario is the Kozai-Lidov oscillations. So the Kozai-Lidov oscillations are due to the fact that some external perturber may induce some oscillations in the eccentricity of the planet, which may increase this eccentricity up to very high values. And so what I plotted here is the time scale of such oscillation as a function of the mass of the perturber and its separation. So one thing we can say is that the time scale of this oscillation must be lower than the edge of the system. So if we plot the edge of the system, it means that we can exclude this region where the time scales are higher. We have another constraint which comes from the sphere detection limit. So we can say that every planet that are in this region would have already been detected by sphere, so we can also exclude this region. So at the end, we are left with this region. But however, we still have some stellar companion, which turns out to be orbiting around the star at a very, very high separation, but still it is orbiting. And this stellar companion is really at the limit here, you can see. Since we have very few information about the system, it is possible that the separation we estimate for the system, which comes from the scale projective separation, turns out to be actually lower, because the scale projective separation is not the same thing as the semi-major axis as displayed here. So at the end, the scale projective separation, in the most favorable case, could be half the current estimated value, which would place this star to this area, which would make this star a possible perturber in the Kozai-Lidov scenario. But this is, however, still a very unlikely scenario, because it would require the planet to have a very, very high eccentricity. So, sorry, the star around 1, and which is very unlikely. So we need to go for further orbital characterization of this stellar companion in order to confirm this scenario. So talking about this region, we could place some other constraint by using indirect detection method, for example, relative atometry monitoring or relative RV monitoring. So I'm leaving. I don't know how many minutes I am left with. Okay, I'm leaving with the conclusions. Yes.
This is very impressive work. I hear all the time about HiRISE due to the instrumental contribution that Mona El-Morsi had to make this instrument a possibility. My question was about your implications for 51 Eri for the Roman. When are you assuming these observations would be taken? If you look at the orbital period for for 51 Eri, the projected separation is getting much close to the star. So if you looked about optimal timing for these observations?
Sorry,
So the angular separation
Yes.
for 51 Eri B is shrinking with time.
Yes.
And there is a range, depending on which bandpass you look at, it may or may not lie within the dark hole or outside the chronograph mask. And so which epoch is this proposed for?
Which epoch is the, if you look at the orbit, so you mean which epoch is the planet closest to the star?
No, proposed for that you had identified as a possible CGI target.
For the Roman estimation.
Yeah. Sorry. Yeah, this one, yeah.
I think maybe we should talk later.
Sorry, I didn't. Sorry.
So I have a question about the fringing. So it seems to be time variable. Do you know, is the same effect as we see in KPIC?
Yes, it's similar because it's a dichroic filter acting as a Fabry-Perot interferometer, so it's very similar effect.
So the amplitude is varying as the
Yes.
angle of incidence?
Yeah.